As we're winding up the semester, I believe we have, 3 weeks left before Thanksgiving break, and then finals week after that. The last few sessions are going to be on different aspects of computers. Today we're going to discuss what a computer can actually do. What can a computer do? Well, it can process numbers. We all learned binary earlier on in the semester or in previous classes. That's the number system that modern computers use. But it can process numbers. It can add, subtract, multiply, divide. What else can a computer do? Nothing else. A computer can't do anything but process numbers. That's all it can do. We see things on the screen like graphics on this board, or text down below, down here. But those are just encoded numbers. So for text, is encoded using ASCII or Unicode. ASCII stands for American Standard Code for Information Interchange. That was the first standard encoding of text into binary numbers that was widely used. ASCII is 7 bits wide. So there are only 128 code points. Less than a byte. But that includes representations for numbers, letters, a lot of punctuation marks, and a few control characters. Let's see here. Numbers. The representation of numbers, 0 through 9, are encoded starting at 0x 30. Capital A through capital Z is encoded, where is that encoded at? 41. 0x41. Small a to small z start at 0x61. The space is 0x20. Obviously, no, I did not had those memorized. I had to look those up. One does not typically memorize ASCII codes. But yeah, it's just they're processed as numbers, represented in the computer. They are represented with ones and zeros corresponding to those hexadecimal numbers. Just numbers. That's all they are. At least to the computer, that's all they are. When it goes through the process of printing it, the graphics card will translate that code. It's like, oh, okay, I need to translate this into these pixel arrangements. But it's just arbitrary. Is this the ASCII system was developed over a period of time and eventually became standardized. Now, Unicode was developed because, well, as the name implies, American Standard Code for Information Interchange. It was made for American machines and various devices. Unicode takes into account other languages, other alphabets, other systems of writing. So they have 8-bit, 16-bit, and 32-bit encoding systems for Unicode. So they can represent numbers and letters from various writing systems. Like Russian uses the Cyrillic alphabet that contains, I believe, 36 letters. Those are included in Unicode, but not in ASCII. ASCII is American. Though, first 128 points are the ASCII set. But with 32 bits, what is that? 4 billion? Is that right? 4 billion? Possible combinations of characters and symbols, all that fun stuff. So all the characters of the Chinese language, where one character represents a word, the entire language can be encoded in Unicode, which I believe it is. But and have room left over for Korean, for Japanese, for Arabic. 4 billion code points. You can encode a lot of different things. But Another thing that computers seem to do well at pictures / video. Again, encoded as numbers. A picture is made up of picture elements, or pixels. Picture elements, known as pixels, little dots. Most computer monitors have around 100 dots per inch. But the human eye, the typical resolution that is photo quality for, as far as the human eye is concerned, is around 300 dots per inch. So 100 dpi, around 100. It varies from monitor to monitor. And 300 dpi for pictures that you would print out on paper, like at Walmart or Walgreens or whatever, wherever you get your photographs printed at. 300 dpi is sufficient for that. But what about the colors? Each color is represented by 3 elements that make up color. Red, green, and blue. And in a computer, that is, those numbers are typically 8 bits each. So that gives you a total of 16 plus million colors possible. So how many colors can the human eye discern? Not that much. Depends, huh? No, yeah, but there's different shades of blue and different shades of red, you know, and different shades of purple and brown and white and gray and all that sort of stuff. So the human eye, depending on who you ask, 1 to 12 million. I asked ChatGPT earlier how many colors can the human eye discern, and it said 1 million. But I remember reading somewhere, I don't remember the source, that the human eye can distinguish approximately 12.1 million different colors. So it depends on who you ask, whether it's a hallucinating AI or a ophthalmology book. I don't know. But either way, a computer can represent more colors than the human eye can discern. So going greater than 8 bits per red, green, and blue, there's no real reason to, because it already goes beyond the human capability. So no big deal. Another thing that monitors have is a refresh rate. Gaming monitors, what's the refresh rate on a good gaming monitor? 240 hertz? 240 hertz? You know what the human eye sees at? 50. Yeah, 50. So the computer screen is showing you almost 5 frames for every time the human eye effectively takes a picture. Television in America is 29.97 hertz. Europe is 25. And movie theater movies are 24. So so when you go to the movies, each time you see a frame, your eye is seeing it twice. Same with watching TV, or whether it's in America or Europe. There's a weird story as to why it's such an odd number that American TV is 29.97 frames per second. They were trying to make it the timing match the 60 hertz, be 1/2 the frequency of the 60 hertz power from the AC grid, from the power grid, the alternating current into 60 hertz. But there was a screw up in the timing, and it ended up being 29.97 frames per second. So if your video camera is recording at 30 frames per second, and then you play it back on like a VCR or a video player that is expecting 29.97 frames per second, your audio will drift. So the audio won't match up. After a while, the audio will not match the video. European power grid is 50 hertz, and they did get their television to match up half the rate of the power grid. Why movie cameras in Hollywood do 24 frames a second? I have no idea. That's one story I haven't heard. But yeah. Yeah, so pictures, video, text, it's all just encoded numbers. That's all a computer can handle is numbers. It doesn't have visual memory. It does not have oh, that's right, there's audio. Didn't cover that. Audio. .1, I believe, kilohertz. 16 bits per channel. CDs. That's what the CDs do. 22.1, if I'm remembering correctly, samples per second. It measures the audio level at that instance and encodes it as a 16-bit number for the right and left channel, and encodes it on and records it on as ones and zeros on the CD, so a computer can read it. Just as a I don't remember the sample rate, but old style television, what they call POTS, is 8-bit sound. For POTS, which is plain old telephone system. So that's why, if you remember, speaking over a landline, the audio quality wasn't very good compared to listening to a CD or a tape or whatever. That's why it's lower bit rate, lower resolution on the sampling, and probably a slower sample rate as well. But it got the point across for the most part. Now with voice over IP or VoIP, you can have, CD quality sound, and have clearer calls with the digital. This sample rate and sample resolution yields a range of 20 to 20K hertz in sound. Now, some people with sensitive ears can hear beyond that range. I believe at the extreme, the human ear can hear. I want to say it's around 15 to 23 kilohertz. I don't remember where I heard those numbers. But it is beyond the range of CDs, so true audiophiles don't like CDs. They like vinyl records because they're analog and have a greater frequency response. The vibrations of the needle on the record player can exceed 20,000 hertz and fall below 20 hertz. So the quality of sound is superior with vinyl records until the record wears out, because you do have a needle basically dragging along the surface. They do wear out eventually. But yeah, just numbers. Lots of numbers to remember, and of course, you have data compression algorithms that reduce the file size and all that sort of thing. That's one thing that a codec code decode compresses files. So that's a codec stands for code decode. So most of these lectures from here on out are going to be fairly brief. Not a whole lot of material left to cover. I believe next time we are going to be covering instructions for a computer. So we'll have that to look forward to. More ones and zeros. And have a good day. See you Wednesday.